If you shine infrared light on a molecule, it's possible for the molecule to absorb energy from the light. And energy from the light can cause a bond to stretch, and we call that a stretching vibration. You can have other kinds, but we're only going to focus on stretching here. And the stretching vibration of a bond is like the oscillation of a spring. So you can think about a bond as being like a spring. So let's think about this bond right here. So the bond between the carbon and the hydrogen. We're going to model that bond as a spring. So I'm going to attempt to draw a spring in here. So here's the spring. And then let's put in the carbon on one side. So we have the carbon on one side and the hydrogen on the other side. And so the stretching vibration of the bond is like the oscillation of this spring. So if you had a spring and you had two masses on either end of the spring, and if you put some energy, right, if you put some energy in, you can stretch that spring. So you could pull the carbon this way, you could pull the hydrogen that way. So that's just like the stretching of this bond here. And we know that springs also contract, right? So then the spring could pull back in this direction, and you get an oscillation of a spring, which is once again how we model the stretching vibration of a bond. So let's look at the IR spectrum for this molecule. So we're talking about 1 octine here. And if you shine a range of infrared frequencies through a sample of this compound, some of the frequencies are absorbed by the compound. And you can tell which frequencies are absorbed by looking at your infrared spectrum here. So for right now, let's think about these numbers like 3,000 or 4,000. Let's think about those as representing frequencies of light. And so over here we have percent transmittance. And so if you had 100% transmittance, let me go ahead and draw a line up here. So 100% transmittance. So let's say we're talking about this frequency of light. So I look at this frequency of light, I go up to here, right, and I can see I have 100% transmittance. 100% transmittance means all of that light was transmitted through your sample. If all of the light went through your sample, nothing was absorbed. And so this particular frequency was not absorbed by your compound. So if you're talking about less than 100% transmittance, right? So let's say for this frequency right here. So for this frequency, we have this signal here appearing at this frequency. We don't have 100% transmittance. So that means not all of the light went through the compound. Some of it was absorbed, right? So this specific frequency was absorbed by the molecule. And that energy can cause a bond to stretch, and we get a stretching vibration. And actually, this signal corresponds to the bond that we've been talking about. So this signal indicates the stretching of this bond right here. All right, let's think about wave number next. So we just talked about percent transmittance. Let's think about wave number. So I've been calling all these things frequencies, different frequencies of light. And let's see how wave number relates to the frequency of light and also the wavelength of light. So the definition of wave number, here's the symbol for wave number. The definition of wave number is it's equal to 1 over the wavelength in centimeters. Right? So if we had a wavelength of light of 0.002 centimeters, so let's go ahead and plug that in. So a wavelength of light of 0.002 centimeters, what would be the wave number? So let's get out the calculator here and let's do that math. 1 divided by 0.002 is equal to 500. Right, so that's equal to 500. Your units would be 1 over centimeters, or you could write that, meaning the same thing. So that's the wave number. That's the wave number. So if we go over here, right, a wave number of 500, you could think about this corresponding to a particular wavelength of light. And of course, this also relates to frequency because we know that wavelength and frequency are related to each other. So let's get some more room down here. And we know that the wavelength times the frequency, so lambda times nu, is equal to the speed of light. That's equal to c. Right, so if I wanted to solve for the frequency, so solve for nu, the frequency is equal to the speed of light divided by lambda, divided by the wavelength. And that's the same thing as 1 over lambda, right, times the speed of light. 1 over lambda was our definition for wave number. So you could say that the frequency of light is equal to the wave number, right, times the speed of light. So let's go ahead and do that calculation here. So we talked about this as being a particular wavelength, right? We found the wave number. Let's plug that wave number into here, and let's see what we get. So the wave number was 500. Units were 1/centimeters. Multiply that by the speed of light. We need to have the speed of light in centimeters. So that's approximately 3 times 10 to the 10th centimeters per second is the speed of light. Notice what happens to the units. The centimeters cancel. And let's do the math. So let's get some more room over here. So we take the wave number and we multiply that by the speed of light in centimeters. So 3 times 10 to the 10th. And we get 1.5 times 10 to the 13th. So the frequency, right, the frequency would be 1.5 times 10 to the 13th. The units would be, this would be 1/seconds, or you could use hertz for that. So a wave number, right, corresponds to the wavelength, and you can also get the frequency from that. So we had, let me just rewrite this really quickly. So frequency is equal to wave number times the speed of light. And so wave number is equal to the frequency divided by the speed of light. And we'll use this in a later video, so we'll come back to this idea. But for right now, the frequency of light is directly proportional to the wave number. And so you could look at an infrared spectrum. Let me go back up here. You could look at an infrared spectrum and call this down here. You could call this a wave number. You could refer to it as a frequency. You could call it whatever you want, as long as you understand what's going on here. Let's look more in detail at this infrared spectrum, and let's draw a line at approximately 1500 wave numbers right here. And the left side of that line, so we've divided our spectrum into 2 regions. The region on the left is called the diagnostic region. So this is called the diagnostic region of our spectrum. And it's because a signal in this region can be diagnostic for a certain functional group. For example, this signal right here, and if we go down here to the wave number, that signal's at approximately 2100, right, for this wave number here. And that's corresponding to the triple bond here. So this tells us a functional group, right? This tells us that a functional group is present. This triple bond is present, and so it's diagnostic, right? It helps you figure out the structure of their molecule. So you can figure out different functional groups present in molecules using IR spectra. So the right side of this line is called the fingerprint region. So this is the fingerprint region. And it's harder to interpret the fingerprint region. It's much more complicated. It's not as easy to see different signals. It's extremely complicated, but it is unique to each molecule. And so it's like a fingerprint for the molecule. And so you can match up IR spectra. If you have an unknown, you can look at the fingerprint region, and again, it's unique. All these different lines are unique to that molecule. So we have the diagnostic region and the fingerprint region. We're not gonna deal much with the fingerprint region, maybe a little bit. We're gonna focus in on the diagnostic region. We're gonna focus where the signals appear. All right. So I look at the signal, I go down to here, and I get a specific wave number. So the location of the signal is pretty important. I did want to point out that if you look at what I used for the wave number here, right? I kind of changed how I did everything. So the spacing is different. It doesn't really matter. I only did this to fit this video and to make it work for this video. And I'm also going to hand draw all of my IR spectra, and so it's certainly not going to be perfect. The idea is not worry too much about what they give you here for your scaling for the wave number, but think about where the signals appear. So the location of this signal, approximately 2100 wave numbers. You also want to think about the intensity of the signal and the shape of the signal. We'll talk much more about those in later videos. On the next video, we need to develop this idea of bonds as springs a little bit more. So we'll think a little bit about some classical physics.